motivation on simulating, minimizing function. Yeah, you remember that if you follow this kind of dynamics, but due to discretization errors, we had something like if the discretization error was small. I think last time I called it eta, but let's call it 1 over beta, so beta large. Okay. Here there was something which was some. It's not so important. It was something like this. The gradient of some weird function plus some small noise. The noise typically scaled as the square root of what is here. And OK, let's say to smaller order terms, of course. So motivated by, I gave you a reference of a paper. I found out that it's very well explained on Wikipedia page, this thing. If you go to the Wikipedia page of stochastic gradient descent, at the very last of the paper, it explains a bit this, because this noise, it has some coefficient also. Here was this noise was like sigma of x w dot somehow, right? So with this motivation, I said, okay, let's look then in general at a dynamic of this type. Let me put here a factor 2 for sake of simplicity, and so the picture was like that v of x was some nice function, but when you perturb, you will have something like this, okay, a perturbed potential. And we wanted to know in what cases what was the size of the perturbation that allowed us to say that when beta goes to infinity, when this parameter is small, the solution to the SD actually converges to the deterministic limit with this function and not with something else. Because we say that in reality, if these bumps are large enough, small with beta, but large enough, you can make counterexamples. That's what we said. And then I tried to convince you that even if you focus just on the deterministic equation, it can be convenient to write it not as a differential equation, but as a variational inequality. Something is positive, for instance. Okay, if you remember, because in that case, it's enough to pass to the limit in some inequalities, and these in some functional. And this functional didn't depend on time. They were stationary. So we have a dynamics. In general, it's hard to make limit of a dynamics of functions that depends on t. And if you remember a bit the approach, yeah, it was like we had noticed that on RD, for instance, x dot equal to minus the gradient v of x. That was equivalent to asking that v of x naught was bigger or equal than v of xt plus 1/2 the integral of the gradient of v square in xs ds plus 1/2 the integral of the derivative of x dot squared in ds. If you remember, we had noticed that this was equivalent, this inequality was equivalent to this dynamics in RD. And we said, okay, but what is here first makes sense also, for instance, on a metric space. First statement, we can give a meaning to all these objects. And the second statement, it was if we want to pass to the limit here, we should pass to the limit in the gradient of v. And if it's enough, if we want to pass to the limit in the inequality, well, it's enough to pass to the limit, okay, on v. But if you want the gradient of v to converge, of course, you know you need that at least v converges somehow. And then it was enough to get an inequality for gradient of v square. We will receive today this inequality, so next time. But you see, it was just for the function gradient of v square, not for the dynamics, not for a curve that depends on t, just on a function of x. So for instance, if you are in RD, the solution to the gradient flow is a function from time to RD, but gradient v square of x is just a function of RD. So it's much easier. It's like we could pass to a dynamic limit just doing static limits. Okay? And we had make as an example also, very quickly, because today we will see it in a more detail, that since this makes sense on a metric space, if we took Wasserstein space as a metric space, as a function, relative entropy, we could write the Fokker-Planck, the Kolmogorov equation for a differential, for an SDE, as a gradient flow of this entropy. We will retake it today, but maybe you remember more or less what we said last time. And since I think some of you were actually in Professor Seturaman lecture, let me also mention that, for instance, there are some other, we have seen in that lecture some dynamics that was like dtu equal to the Laplacian of u minus f prime of u. Yeah, you may remember this. And this can be regarded as a gradient flow in this metric sense of the function v. So the function will be from L2 to okay, R, maybe union infinity. And v of u is like integral of gradient u square plus f of u in the x. Okay, so if I look at this function on the metric space L2 of x, L2 in space, this dynamics is the gradient flow of this functional on this space in this metric sense. Or another equation we have seen in the lecture was like dtu was, I think here we need a minus, Laplacian of u plus f prime of u. And this will be the gradient flow in this metric sense of actually the same functional, but not in L2, but on the space h minus 1, of a negative sublet space. So what actually, the results that he mentioned for the convergence when he here added some weights, actually you have also to rescale time, but it's not a big deal. It's a big deal to prove the theorems, but not to write it. The results for the conversion of k goes to infinity have really been proved using this scheme. You write the gradient flow as an inequality, and you pass to the limit in the inequality rather than in the gradient flow. Okay? Because again, here there are functions of times that are always very hard to deal with, and you can reduce to just making some variational limit. So, okay. In any case, back to us. So we had like this problem motivated from saying discretization errors in stochastic gradient descents, or in just gradient descents. And since I'm a bad person, I said, okay, instead of looking this an Rn with some weight, whatever, with all this blah, 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 just let's consider the same formalism, but maybe on a manifold, okay? So that the coefficients of the noise are embedded in the definition of the Brownian motion. So let me, since this I know that is always kind of confusing to people, I'm saying that M is a Riemannian manifold. And I will take it compact, okay? And just let me remember you the very basic notions in differential geometry, which is also all the notions in differential geometry I know, more or less. So the first thing is, so you can think that, I don't know, you are on a sphere, for instance, or maybe a torus, but your Brownian motion has a coefficient, okay? So what we have, actually, I prefer to use what's the inverse Riemannian metric. Let's call it A. So, okay. First, in each point x, we have the space of tangent vectors in x. Okay? That depends on x. And then you have the space of cotangent vectors on x that are just linear function on the vectors in x. So they're just, again, they are just vectors, okay? But just a map that to each x associate a tangent vector, that's called the vector field, or tangent vector field. And the map that to x associates a cotangent vector is just called a one form. Okay? So they're just vectors, if you don't like to think of geometry. They're just vectors that depends on x with the same dimension as the dimension of the manifold. But, okay, and they depends kind of nicely on x. What else we have? We have on a Riemannian manifold. So A of x is just a map that for each x take a cotangent vectors and give you a tangent vector in a linear way. Okay? So in particular, you can do something like omega square, and this is invertible. It's an invertible map, okay? Symmetric invertible map. So you can think that omega square, okay, will be just a norm in a point x. In a point x, omega square is just the square of a norm on the cotangent bundle, which is just a omega x. This is tangent vector, so I know what is by duality on the tangent, and that's just this thing, okay? So it's just a way of introducing a norm either on the tangent bundle or the cotangent one. Because also E square will be, this is symmetric, okay, this is, E square will just be a minus 1, okay, in x, everything in x, e. Okay? So these are just the functions on x, which is the norm of this vector on x. Given this a, which is like, if you write it in coordinate, so where it was. If you write in coordinate the Brownian motion, a would be like sigma sigma joint, okay? It's just a way of deciding these norms. And then on a Riemannian manifold, there is something called the volume, which is just a measure on the manifold, which just corresponds to the idea that, you know, I take a small vector on the tangent bundle, another small vector on the tangent bundle, and I can more or less say what is the surface of an infinitesimally small area that they somehow span. It's sort of what you would do for the Lebesgue measure in RD. And just if you choose, you know, what is a manifold, it's something that locally is like RD. Okay? So you have like a locally, if you make a small enough open set, this thing, there is a invertible smooth map in both sides that really looks, that maps points to an open set in RD. And then, so if you fix coordinates here, this will give you some coordinates on the original manifold, okay? So the volume of x, the easiest thing is to write it in coordinates. It's just some fixed measure, reference measure, which is like in coordinates, is like 1 over square root of the determinant of this a. So I will take this a non-degenerate, like really a matrix which emits a tensor which emits an inverse, okay? You could take it kind of degenerate, and that's called the pseudo-Riemannian case, basically. dx1, dxd. So like up to some coefficient which is not important, it's basically the equivalent here of the Lebesgue measure. Okay? And then we have some basic operation which are like taking the divergence and doing this kind of thing. So I think that if you have a function, smooth function, from n to r, that's like a zero form. You can associate to it the differential of f. I think we actually discussed a little bit last time. This is a one form. This gives you one form on the manifold. This means that to each x, you have it associates a cotangent vector in x. That's called the differential of the function, right? And then you have, so this differential goes from zero forms to one forms, right? That's what the differential does. And you have an adjoint differential. This doesn't depend on anything, on the matrix, on nothing, okay? It's just you take the differential. But it's adjoint. It will take one forms and will give you zero forms. And that's basically, okay. And it's defined in the following way, that if I integrate, so how is defined? It's defined weakly. If I do a omega df, so for each one form, okay, when I integrate a omega df, this is just minus m of this star omega f for every f, smooth. It's just it's defined by an integration by parts formula. Okay, so it's like the divergence of a omega. But since there are all these square roots, if you write the divergence in coordinate, there will be some square root of the determinant appearing. That's why I prefer to write it everything weakly, because it's quicker. Is it clear what's this? If we are on RD, okay, if we are in RD, this star omega, this is a vector field with a flat matrix. This is just sort of divergence. The sum of the di omega I. It's just the divergence. In general, it's like the divergence of a omega, but in the divergence, you have some square root of it. So that's for what we need, and I think it's. I think that's it. And then we have checked what is the space of one currents, and these were linear. So like linear functions. Functional on one forms. So it's just, it's just something that to each omega associate a number, j of omega. How should we think about it? It's like a vector of distributions. like a vector of distributions, yes? Because omega is a vector field, so what's a linear function? Okay, continuous, yeah, if you take continuous on the space of smooth one form. So I didn't write, but our space is compact, so if you take like a zero current, is just a distribution, is a linear function on the space of zero forms, so just a distribution. But since one form are vectors of functions, one current is a vector of distributions. Is it okay, this idea? For instance, I don't know, if example, E is a vector field, smooth, whatever, vector field. Mu is a measure on M. Then I can take if I define J omega equal to mu of E omega, that's a current. Okay? It's just you integrate in the mu EI sum of EI omega I locally. That's the simplest current you can do. Very well. And then, okay. So when I write on the manifold x dot equal to b of x plus square root of 2 over beta w dot, okay, this I think on Rn is clear to everybody what it means, this equation, right? So here what I mean on the manifold, I just mean the Markov process generated by the operator, okay, the closure of this operator, but you can define on smooth functions LF on x, okay, 1 over beta, the Laplacian of f, plus BDF. So remember, B is a tangent vector field, which is smooth and given once and for all. I can look at this operator. Okay. I forgot to define what is the Laplacian of f. I tell you immediately where. Delta f is just d star df. So if you have a smooth function, df is a smooth one form, and d star df is a smooth function. Okay, I think we checked in coordinates. This was just a square root of a, because this is the di aij of a square root of a. So this is the determinant, djf. So it's just like this, okay? So if, for instance, this determinant is 1, that's basically more or less like the, I don't know what to say. You can always, locally, when you go to RD, you can always reduce to some b of x plus sigma of x w dot Gaussian, just what is, just, you know, in this b there are a few derivatives of this vector ai, of this tensor aij. Because if you want to write with the Gaussian sigma of x, you know, the generator will be the trace of a dash of f. So, like up to changing the name of b, locally you can always come back to familiar SD on RD. Okay, just this is more comfortable to avoid all this derivative of a blah blah to write this as your usual Ito formula. Okay. So what does it mean that x dot is Markov process generated by this operator? It means that for each mu, which is a probability, so I don't know, fact, which I will not prove. For each mu, which is a probability on M, there is a probability measure on continuous functions with values in M. Okay, the maps that to mu associated with mu is measurable, such that P mu is Markov. The probability, so this is a probability measure on paths, on functions of time. Right? So the probability measure that at time 0 you are in some set, that's just mu of the set. So this parameter mu is just the law at time 0. Okay, it's just the law of the starting of the initial condition. And finally, d in dt of the expected value mu of f of xt computed when t is equal to 0. That's just Okay, okay, mu of LF. Yeah. That's yes, absolutely. Yeah, that's yes, absolutely. If you are more comfortable, you are right. That means that f of xt minus f of x naught minus the integral between 0 and t of LF of xs ds is a martingale. So you can build it pathwise and check by Ito formula. That's just Ito formula. This is a martingale, or you can have an analytic approach. Just take this operator and prove that it satisfies what's called Hille-Yoshida conditions, and so it generates a semigroup to which is associated a nice Markov process, where nice here means, for instance, Feller. If this word don't tell anything to you, is absolutely not important to us. Okay. So this definition, actually, this as I understand Ito formula, you have seen. So this is just how you write Ito formula for a general Markov process, just that there is some linear operator, which is called the generator of the Markov process, and that in this case, on smooth functions, at this form. So I have absolutely nothing if you think that this is your favorite SD on RD. Just the notation is more convenient with this star and whatever it is. So probably you know then Kolmogorov equation, or Fokker-Planck equation, no? That one can write in a bit abstract way. Like, so if mu t is the law of xt, you know that dt mu is like mu t L. What does it mean? It means that for every f, so for every like zero form, yes, the derivative in time of the integral of f in the mu t is mu t of LF. That's actually a consequence of the definition of the generator. Is it okay? So you can do an exercise, always useful exercise. Assume that mu t has a density with respect to volume, which you can think is Lebesgue and you are on RD. Okay? Then find a PDE for rho t. You just write this, integrate by parts the derivative on f, and this will give you a PDE for rho t, which is called the Fokker-Planck equation indeed. What else I wanted to say? So yeah, I want to take a bit of an abstract stance. What is mu t? What is the law of the process? We can think like this, no? That is the expected value of the delta over xt. What does it mean? It means that every time I test it against a function, I guess the expected value of the test of the delta of xt over the function that is f of xt. Yeah, that's the equation that identifies this measure. Okay. And then the same way as I define the law of xt, I would like to define a current associated to xt, which I will call like the typical current, probably, typical current. So I want to do the same thing, but let me be a bit formal. Then we will define this typical current. And I want to define a current Jt. Yeah, let's call it Jt of omega as the expected value when I start, okay, with the law of mu. Here also mu t, yeah, I start with some law of mu 0 times 0, okay? So mu t will be the solution with this, with given initial condition mu naught, for instance. So this will be, sorry, Jt. And let me write it in this way. Delta in xt dxt. Okay. So what does it mean? The same here. Here, like for each function, for its zero form, that's what it means. And here, it's better to write it integrated in time. So this means also that it means Jt of omega is the expected value when I start with this law, whatever it is, of the integral between 0 and t of omega of x, the integral between 0 and t of this is this stochastic integral. So, as I understood, not everybody is familiar with the Stratonovich stochastic integral, which you can define in 1 million different ways, a bit like Ito, but taking the middle point in the summation, or there is at least on reasonable spaces, there is a characterization now as what's called the geometric rough path. But we are going to look at a different idea to just have an idea of what it is. Okay, so here I didn't need to integrate in time. It has a meaning point-wise, but this integral inside is better to write it integrated in time. So this current, I define it weakly for every one form. Okay, like here I define the law of xt as that probability measure. If you want that distribution on function, that distribution on zero forms for which this is true for every f. Here I define a current, the current of xt, as that current such that for each test one form, this formula is true. Okay, where this is Stratonovich integral. What is like a 10-second definition of Stratonovich integral? Because we will not need, we just need this. So defining the Stratonovich integral is complicated, but defining its expectation, it's easy. So we will check in a moment. But just to have an idea as a motivation, where does this come from? This object, okay, is the following thing. You have your manifold. For instance, you have RD and the Brownian motion, or you have your manifold and the stochastic process with that generator. Okay, you know that you can, like you have probably seen the Donsker theorem that if you make a random walk and you rescale properly time and space, you will converge to a Brownian motion, right? So okay, it converges to a Brownian motion. But then if I have so I can always do this. I can always discretize my space and make a random walk that converges to Brownian motion, which is symmetric, or to a process like that one with a given my given generator. This is on any space. You can always make discretize things in such a way that there is such a convergence. And so instead of looking at the law of of the process. Okay, so where you are at each time, on which vertex you are at each time, you can count up to time t. You fix an edge, and you can count up to time t how many times you jumped across from this point to this point, minus how many times you jumped from this point to this point. Okay, so this means that like the discrete current, say a discrete current will be, so you have a graph, okay, will be just a function or a measure on the edges of the graph, not on the vertices, but on the edges of the graph, such that, so as the empirical discrete current, like if you give me a random walk on this graph, the empirical current up to time t, in the interval 0t, okay, this will be a measure on the edges. So let me first write the formula, and then I tell you what it counts. So so you take it's like a distribution. So then in this discrete case, the distribution is like a function. It's a distribution on the functions over the edges of the graph, okay, that acts on functions that are antisymmetric. So xi on the edge xy is minus xi on the edge yx. So for instance, if I take xi xy equal to okay, 1 if xy is one edge, minus 1 if it's minus that edge, so if it's the one reverse, and 0 otherwise. Okay, on this guy, this j counts. Maybe this notation is not familiar. Sorry, counts how many times I jumped across this edge minus how many times jumps in the reverse direction. So sorry, this sum, I should have said before, I sum over all the time before t of where was x before, just before time s, and where is x at time s. Okay, so that's exactly, if I make this jump, okay, I count, every time I jump, I count exactly xi of that jump. Since xi is 0 when x is equal to y, by this property, uncountable sum of 0 means 0. So that's a very standard notation. Maybe you have seen it for Markov chain, Markov processes. Okay, is not, okay? So a discrete current just is an object that, on a graph that just counts how many times you jump across an edge. So if you so then like J0t of xi, if you make the same scaling as Donsker theorem, so you take your process, you take your Markov process that converges to your continuous diffusion. Okay, we know that the law of the process converges, for instance, to the law of this guy, or you can think just Brownian motion. Okay, where does? But this, I want to know more. I don't want to know where the process converges. I want to know where this current converges. How many times it jumps across the edges. Okay, I put here a counter, and I want to know how many times my process passes through that edge. Sure. Not really, I think, because local time is there is more information in the current than in the local time to some extent. So, okay. So this, okay, will converge to the integral between 0 and t of omega of xs in the xs in the scaling when the law of x and converge to x, provided. So xi, you see, is a function of x and y, so you will need that that xi in some sense represents the one form omega. Okay, so it's like this Stratonovich integral just tells you how much kind of is a sort of a, you know, it's, you certainly can if your curve xs was smooth, yeah, you can compute this integral, right? You have a one form scalar x dot in the S. This is called the integral over the curve x of the one form omega over the curve x in the interval 0t. Right? So it's just is exactly this object, but when x is not so smooth. Okay, you can define it, for instance, if x is a class C alpha for any strictly positive alpha. It's not really something stochastic. So just if you are discrete, you make this curvilinear integral by discrete steps. When your Markov process converges to a diffusion process, if you rescale n, this discrete current, this discrete integral along the curve will converge to this Stratonovich integral. Is it complicated? No, because if you have seen Ito integral, it's very easy, and that's here why I defined this star. Okay, the point is this, no? So the only thing you should remember about this integral, if you want, is the following fact, that if dx is b dt plus dwt, okay, so the part in dB, I think it's clear for everybody. This would be omega of xs b, well, I should write it in the inverse order, omega of xs in the S. Yeah, like if x dot was just b without noise, it's clear that there is that's what it means. Then there is the part dwt, right? So that's like not so important for us, but it's like Ito. That's dws. So we are not so important. Okay, there is a square root of 2 of a beta. for us, this is not important what it is, except that its expectation is 0, is a martingale. But then, that would be like if this guy was Ito. But then there is a difference between Ito and Stratonovich, which is just 1 over beta d star omega of xs in ds. So it's just your Ito integral, but up to this correction term. So if you are in RD, indeed, to correct from Ito to Stratonovich, you just need the divergence of the vector field. But if you have this coefficient, say square root modulus of the determinant, blah, blah, there is this guy. That's all I wanted to say, okay, on this. So in other words, okay, this was just chatting. But let's then, okay, so we have then the first definition. The typical current associated to x t solution to this SDE is jt of omega equal to, well, we have to take the expectation of this guy, which is written exactly the expectation of this guy, which is written here. This is a martingale, goes away, right? And these are all, I can take the expectation inside the integral in time, so that the formula all to the left will actually hold. If I take jt of omega as mu t of b omega plus 1 over beta d star omega, where mu t is the law of xt. You can immediately check that if I plug these on the left-hand side here, I will have all the equalities. Okay, so all these, the Markov process, blah, blah, are just ideas why I introduced this object and why I introduced this definition. But then the definition is just I define this current. Just that's why, you see, if mu t is not regular, this is just a distribution on currents. Here there are derivatives. It's not a measure. Yeah, really there are derivatives. If mu is not smooth. Okay, so it's also useful for mu to introduce this notation. For mu, a probability measure on M, or more in general, a distribution. Why not on M? Denote J mu, okay, the current mu of b omega plus 1 over beta d star omega. So why did I make all this little discussion with the Markov process, with the Donsker theorem and so on? Because is it okay? Is it okay? So let me define then. Let me give another definition. Okay. Let U be the space so U will be the space of pairs. So let me, since we are at the blackboard, is a bit so let me mu underscore then J underscore like be functions of time. Okay, I will write it. Okay, but if I write mu without a trait, that just means a measure. J without a trait just means a measure. Right? Mu J means functions of time. So this is like the function of time mu t, and this is the function of time jt. Okay, so mu will be, say, a function of time which is continuous with values in the space of probability measure, or more in general distributions over over our manifold, and J will be just a map, measurable, with values in one currents. Let me be slightly sloppy on the topology of this space. I didn't write the main equation such that dt mu t of f, okay, the integral in dt mu of f, is jt of the f. So I wrote it weakly, but you should interpret this as dt mu plus a sort of a divergence, okay, let's call it divergence of j equal to 0, a continuity equation. Even better way is to think that your manifold is a product times time space, and this is just a time space current with whose divergence is 0, because dt mu is just the divergence in the time direction, but okay. Okay, so these are the pair current, measure currents that satisfy continuity equation. Does this continuity equation speaks to you? You have seen it like it. If you have a conserved quantity, yeah, there is an associated current for which it satisfies a continuity equation. It's a very. Is it okay? Just this. In this form, I'm sure you have seen dt rho plus divergence of 0 equals 0. I'm sure you have seen it in some class of mathematical physics. So that's exactly the same thing. So is it true that, instead of looking, okay. Now what I claim, if mu t, jt are the law and current of xt, typical current of xt, then mu j are in U. What I should check? I should check that dt mu of f, dt mu t of f, is equal to jt of the f. Okay, nothing more, nothing less than that. So indeed, this is true, this holds. It's okay. So mu t is the law, namely. Okay. So proof is very quick. Who is j mu of df? J mu is there. It's mu of 1 over beta d star of df plus bdf. That is mu of LF. On the other, so jt, the current of x, typical current of x, is just j, this j here. Yeah, this is a bad, with low mu t, with measure mu t. It's this definition here. Yeah, it's sorry. This wanted to be a sort of calligraphic j probably. So j, big J with index mu means this measure. Okay. So if I compute it on exact forms on df, this gives me just mu of LF. So when I take now as current jt j mu t, I get that jt, the typical current of df, is just mu t of LF. And since mu t is the law of x, so that this is just Kolmogorov equation. Okay, the fact that dt mu of f is jt of LF, namely mu t of LF, is nothing but the Kolmogorov equation. So the pair law of xt, current of xt, satisfy the continuity equation. This is not surprising because they already satisfied the mu t was the expected value of the delta in xt. Jt was the expected value of this Stratonovich integral, and already they were expected values. But this equation is already true at the empirical level. It's true almost surely. it's, you know, if you think of this discrete process, if psi of xy, so in this example, yeah, if psi of x and y was some function in y minus some function in x, which is a one form that represents df, in this sense. You see, if I do dy f of y minus f of x, I just get df. You see that j 0t in x is nothing but f of xt minus f in x naught in df. Yeah, because this is a telescopic sum. Every time I jump, I add f of x where I jump minus f of x where I was. So it's a telescopic sum. Okay, so that's that's exactly the integral between 0 and t of dt of the delta in xt applied in f, if you want. No? So that's exactly a dt. So delta in xt, the derivative in t of delta in xt is this integrated current, and so that's for each element, like with probability 1, this was true already before taking the expectation. So also for the law of xt and the typical current of xt, it will become true trivially. But we checked it. And OK, what you have to take in mind is just this definition, and that claim, and this definition of u. OK. So, so in some sense, what I'm trying to say to make it all this, why all this definition, instead of saying that mu t is the law of xt, so one can say mu t is the law of xt, it solves Kolmogorov equation, no? Solves. Okay, that's a statement, a theorem. That's basically Ito formula. What tells you Ito formula? Tells you that the law of xt satisfies Ito equation. You take expectation on the Ito formula, and that's the statement. Okay. Here, what we say that we make so what we just proved, okay, is the following fact: that if mu t, jt is the pair law and current of xt, then this is in U by definition somehow. That's the space where we are. But the statement is that jt. So what replaces Kolmogorov equation for us is that this is this calligraphic j mu t. So a stronger statement than, so theorem 0 is Kolmogorov equation holds. I make a stronger statement. My stronger statement is that the low current of xt are an element of our space U, and the statement is that jt, the current of xt, is this calligraphic j with index mu t, which is exactly the law of xt. Why I say it's a stronger statement? Because this means that for every omega, gt of omega is this j mu t of omega. For every omega. That's what this statement means. If I check this statement only on exact one forms, not on all one forms, on when omega is df, I get Kolmogorov equation. So Kolmogorov equation is a corollary of this equation. On the other hand, from Kolmogorov equation, if I know Kolmogorov equation, I don't know the current of xt. I only know the divergence of the current of xt, because I only know this divergence on exact forms. Okay, so this is somehow a stronger statement. So when you, is it okay? Okay. I'm quite late. So, so what I want to introduce now is then, instead of making converge then the law of xt, or if it's trapped, not trapped in these bumps and so on, the law of xt, I want to make converge the pair law of xt, current of xt, which is a stronger statement. If you check this convergence, not on one forms, but on exact one forms, you get the standard result, which is like convergence of the law of xt. So to this aim, so now I want to kind of write this equality, which you should think like a differential equation, as an inequality. Why? Because I want to pass to the limit under some singular limit. Is it clear, the picture where I'm going, okay? And okay, to this aim, let's us define definition. This is for me sort of a Lagrangian. So define L will be a function that takes a probability measure or a distribution times a current to 0 infinity. No. Let's first define a norm. Sorry. Let's first define the space L2 of mu. So this is a space L2, but not of functions of currents. When I say that the current's in L2, so J, which is a current, because this is just a distribution, no? But I want to say when it is in L2, is in L2 if this norm is finite. J mu square, that's the sup over all one forms of J of omega minus 1/2 mu of A omega omega. Okay. What does it mean? You can, okay, exercise or example as you want. If J of omega is mu of some vector field scalar omega, then the norm mu of J squared is mu of, so A minus 1, A minus 1 E. Okay. So it's like the L2 norm of the vector E in the mu. Okay. But many distributional currents will have this supremum equal to plus infinity. For instance, they make derivatives or something weird. This will be plus infinity. Okay. Okay. So and then I define a sort of a Lagrangian. Okay. L of mu and J. Let me write this. So this takes a probability and takes a current and gives me a number between 0 and infinity. L of mu and J. So I would just say that this is the norm of J minus J mu, where J mu is this calligraphic J mu, squared mu, the L2 norm of this difference. I would like to say like this. I need to be slightly careful if, let's say that if J is in L2 and plus infinity otherwise. Well, I need to be slightly careful because it could be that J minus J mu is in L2, but not J and J mu separately. Okay. And then I define an action functional. So A, this will go, so A depends on T, depends on T, but I will drop this index T. This takes U, okay, my space of pairs, currents, and measure, and gives me a number from 0 and infinity. Okay, A of mu J is nothing but the integral between 0 and T of L of mu T Jt in dt. Okay. Where does this come from? Well, many years ago, Claudio, with several collaborators, they published a series of papers where they suggested that this is not really mathematics, it's more meta-mathematics, that when you have non-reversible dynamics, when you have a kind of complicated statistical systems, the large deviation rates of the pair empirical measure, empirical currents, is the dynamical equivalent of what these thermodynamic functional, like free energy that you may have studied in high school, are for a reversible system at equilibrium. Is a sort of a dynamical counterpart of the thermodynamic functional. So to get this rate, this is the simplest possible you can do. If you take n independent particles, each one satisfying this SDE, okay? If you take the empirical measure in n, and the empirical, the empirical measure in n. This is a path of probability measure. And you take the empirical current. So let's write with this notation that we used. Okay. This object will make a large deviation functional with this rate, well, maybe 1/2 this rate, when n goes to infinity. Okay, this beta we will put it later, but okay, for beta equal 1, okay? This thing, if there was some interaction, you just need to modify this L. But most of the things I say will stay similar. So just you will not get linear currents and so on. And you will not in general, okay, but say, similar action functionals, not the same. Similar holds for many interacting particle systems. Okay? And this is an interesting functional. We will not care who is this functional except for one fact, that how do we characterize the solution? I'm very late. How do we characterize the pair law of x, current of x? So, a trivial statement. So, remark. Jt is j mu t, okay, if and only, so mu t jt is the law of xt and the jt is if and only if a of mu j is equal to 0, okay? Because A is already defined on the space U. All my pairs only live in this space that satisfy them the continuity equation, okay? So this A is 0 if and only if J is J mu t for almost every t, and so, okay? Or if you want, even better, only if this is non-positive, okay? Only if this is non-positive. I want inequalities. Being the current of x, mu is the law of xt, and jt is the current of xt if and only if this action functional is non-positive. Because certainly it's non-negative, it's always positive. So if it's non-positive, if it's less or equal than 0, then it's 0 and j is j mu t. And then and then I introduce some functions, and then I let you go. The first is h beta of mu. This we have already seen. Oh, okay, not important. 1 over beta, h of mu given m beta, and beta is the invariant measure of x. And then I define I beta of mu, which is 1 over beta squared, the integral between 0, the integral in dm of d mu in dm beta square over d mu in dm beta in dm beta. So that's the density. Gradient. So let's be, okay, maybe I can be a bit more precise and take one extra minute. Let's say this is gradient rho square over rho if mu beta has density rho with respect to m beta and plus infinity otherwise. Yeah, I should say what is the gradient of rho here, or let's say the differential is better, d rho square. But it will be clear from the next statement. Okay, this thing will make sense. Don't worry, we will have another form for this I beta. Then the next thing I want to prove, next time is the following statement, and this is the statement on which we pass to the limit, is that A of mu and j, so if h of mu and j is finite, if A is finite, A of mu and j is finite, then, so let's say theorem, okay, theorem. If h of mu and j is finite, then h of mu and j is h of mu t, h beta of mu t. So this beta was in j, this guy depends on beta, remember, minus h b of mu 0. Yeah, I also need that h of mu 0 is finite, I'm sorry. H beta of mu 0 infinite, plus the integral between 0 and t of I beta of mu s ds, plus the integral between 0 and t of j s minus r mu s square mu s ds, where r mu of omega is nothing but mu of b plus or minus the gradient minus of the log of dm beta in the wall. Okay, some function omega. So you see that. So what? So this is what's the end of what we were saying today. We started that we want to characterize a dynamic as an inequality. Since mu j is what we want, even if this is negative, okay? So we get that mu j is law and current of xt, if and only if h beta of mu naught is bigger or equal than h beta of mu t plus the integral of I plus the integral of this for every t. And then we pass to the limit in this inequality to find if we are trapped or not. In principle, you can do a similar argument for interacting systems. Maybe I should have, it was easier to mention the PD than the stochastics, than the interacting part, the stochastic. So you can recover this action function as large deviations of some simple stochastic PD. So independence means that this PD is linear. Squared. Okay. So then next time we will prove this statement, which is very simple to prove. And then pass to the inequality in here. Maybe I want to say some words about gamma convergence. And now, in the reversible case, this guy is 0. And this guy is exactly the gradient of the entropy in the Wasserstein-2 space. So this is really the formulation of reversible Fokker-Planck equations as a gradient flow in W2. I don't know if you remember this. We mentioned this last time. So this I beta is actually the gradient squared of the relative entropy. Mu and oh, yes. This every A is defined on U. Is defined on pairs that satisfy. So yeah. Mu and j, there do not. This is our space. The space, everything mu j are always in this space. They live in this space. Any pair mu j. They don't exist. The space of mu j out of they don't satisfy continuity. Doesn't interest us. You could take time out of the equation and just use the stopping time instead. It's dt plus L is like the generator of the Markov process txt, no? You can always take this point of view. So, okay, I was maybe gave too much examples and too little formulas, but we will prove this statement next time. Okay, we will introduce these currents a bit more in detail and pass to the limit.